Welcome back, everybody. We are in week 6. I'm going to jump around from the syllabus. I know in the syllabus, I believe it says after our, sorry, after chapter 9 and 10, we go to chapter 11, computing the areas. I actually want to get the point of emphasis down to chapter 17 and 18, topographic mapping, because that's one of the more key things that you guys are going to have to do. I know right now, currently, we're working with the Traverse, so we're still working with that. So, lab wise, continue on with the Traverse, and then we will move on to the mapping or topographic mapping later on in the term. But for lecture side, we're just going to get into it now, get on to the whole reason and the theory and all the good stuff. So that's what we're going to be picking up on is topographic mapping. So sorry. So spring 2025 course, we are topographic surveys. So the definitions, so I'll go through this slideshow presentation and I'll also go through the Pearson book and talk about the characteristics of topographic survey. The slideshow, more of a visual aid for you guys, kind of just go through everything of all the visual aid or the representation, physical representation of contours, what they look like in a profile side and in a plan side, and just kind of definitions of different runs or layouts on maps. All right, so definitions. We're going to have contour lines. We're going to have contour intervals. We're going to have intermediate and index contours. We have grade slopes, which is rise over run in a percent format. We have grade break or line break line, and we have planimetric features. So looking at it on a profile side or a hillside, right? We have this hill we're looking from the profile side, and we start here at the bottom, kind of bowls here, got a bowl here, and then it rises here, another little valley through here, and it rises again, right? And if we were to put that with numbers or elevations, we could see how it would rise on a profile side, right? So we just started somewhere down here, under 235, and it comes up and it rises, right? We don't know the distance. We don't have distance. We just worry about elevation on this side. And it comes up to right about 280 in this area, and it comes right back down to 240. And then again, it starts climbing, and it gets up to right in between 295 and 300, and it starts to descend again. So in that aspect, we would want to be able to take measurements along this thing. Let's say we would need it to take this huge, maybe it's a short run, it's just a difference of almost 70 feet there, 65 feet. So if we needed to get those grade breaks in there for whatever reason, it'd be important to hit, bottom, maybe a bowl side here, one shot here, maybe one here, and then one here to define this hillside. And that way you can define, if you took a shot here, here, and here, and then these 3 shots here, you could define that slope and you could define the contours along that as it's running up and down that hillside. And then the same thing, it's also a little bit more uniform as it's going down. So maybe you just need a shot here, here, and here. And then again, but again, it'd calculate that slope as it's coming down and then going back up. And then, you kind of have a small grade break right here where it's not uniform. It comes up and then it kind of angle points the elevation and it comes up again and then it goes down again. So just another visual aid here, kind of like a plan side and then the profile side, or sorry, profile side up here, plan side down here. We're putting this in units, 100-meter units. So we have, as you can see here, the more spaced out these contours are, the more of the gradual slope it is, or a gentle slope. Or on this back side, it's a little close. These contours get a little closer together. It's more of a steeper slope. All right. So that's the representation on the profile side. If you look at it on the plan side, it looks something like this. The distance in climb or the elevation climb. You can see how far out the distances between these two, between 50 and 100 meters. But at the same time, you come around the backside of this hill, and right here, between 150 and 50 meters, this climb, I mean, it's the distance there is very So it's a lot steeper, right, in that area, right? It's a lot closer the distance wise. So it's steep on that backside, and out here it's more of that gentle slope. All right. So a couple rules or the characteristics going for them. Rules for contour lines. Contour lines are parallel or concentric. They close together. All right. So contour lines equal close together. Contour lines equal steep slope. Far about contour lines is a flat slope or flatter slope or a gentle slope. Contour lines do not cross. Number one rule there, they never cross. So if you're ever working on a topographic survey or you do a topographic survey, take it back to the office and you start producing your contours in the office, you got to make sure your contours are not crossing, because then there's something wrong with your shots. Something either there's a rod bust in there, or you took one too many shots and you crossed your line. Something happened, right? And you got to make sure that your lines are not crossing. Creeks, draws, and ridge lines, they're very obvious with contours because they make a uniform, kind of just like a V shape one way or the other, or a U shape. Saddles are two peaks together, and then we have depressions, kind of like a bowl, right? And we'll go over visual aids on those ones. So just from the book here itself, just another representation. If we have kind of like a profile side of the climb, right? I mean, just to put a representation of a hillside, you have your distances between A through E, and then you have your vertical climb from 10 to 60. That's what it would look like on a plan side of it, right? If you're looking on one side to the other, from A to big C, if you look at it on the plan view, that's what it looks like over aerial view, right? Same thing here on the profile view. You see that climb, it's coming up here. Same thing, it gets a little flatter here, but then it bowls and climbs again. So, I mean, that is just another good characteristics of how contours work. Again, the flatter, the further away contours are, as you can see here on the plan side, you look here, the less, the flatter the elevation is in that area. But the closer it is, kind of like between B and C here, the bigger or the steeper the climb. And so again, the contours are parallel or concentric. They close on each other, right? So again, you have a huge steep climb here, and so you see that those contours are close together. They're concentric. They're parallel with each other, and they run on around the entire hillside there. And the same thing, we have a wider shot or a wider hill here, and you can see the characteristics of this hill, how the contours widen out a little bit more. So whenever you do these topographic surveys, you want to reflect the physical representations. So with taking any topographic surveys on this type of style, wherever these grade breaks are at is where you would want to take measurements. And then as well as here, you would want to take one on each side and the top of the peak of this hill. And then same thing here, you have kind of a small grade breaks here, but if you have a uniform representation, you can kind of skip that part, because if it's uniform slope, it's just going to be the same percentage down or the same slope all the way through. But again, if you have something kind of like on this left-hand side, kind of just a little bit of grade breaks where it flans out a little bit and then climbs back up, you want to take those measurements. And so with like this area, again, same thing, you would want to have a measurement here, maybe one or two in the middle, and then another one on the other side of that hillside, just to make sure you portray the characteristics of that hillside or whatever it is correctly. And then again, another visual aid here. We have the steep slope on this backside where B's at, right? And you see how close those contours are together and how it's climbing really fast. And at the same time, on this other side of it, where A's at, kind of the northern side of it, contours are further apart, flatter, and it makes it just an easier way to climb. So whenever you're looking at these maps, that's kind of the one thing you want to do is just kind of look at that representation of the contours. You look at those USGS maps or anything like that, and you go, okay, well, what's it looking like? Oh, excuse me. Climb wise, what's the slope looking like? Is it steep, gentle? What's the easiest point of access through there? And so that's one of the biggest characteristics that contours can provide for you. Looking at it with like a digital model. So you have the plan view here, kind of just what we show a 2D type of representation with the contours. You can see it's how very steep, right? And then, but at the same time, inside that bowl area, it's very flat through there. But then you look at the, area here on this representation. Again, you see that it's pretty flat inside that mountainside through there. This old, just a scannable volcano. I believe this is Mount St. Helens. I believe. Don't, if I get it wrong, I just, I grabbed this one from a image, good image that I saw, or actually one of the professors gave me. So I was it's just a good representation of what like a digital model can show you of, how it flattens out here, and then you get inside that bowl or inside that caldera area. It just has, steep walls along that inside, and then, the other side is just the whole thing is just steep, but again, flatter. It's on the outside of the base. And as you start to climb, obviously, it just gets steeper and steeper. All right. And then saddles, you got two hills, right? Representation of two hills. You have, again, a flatter slope here through this area, and it climbs a little bit more. And this, as you get up there, and the same thing, we have a little valley right here, the peak here, a valley through here, as you can see by these contours, how they're kind of making that V shape, and then another hillside there. So we have what we call a saddle through there. And then the aerial view of that saddle, same thing, what it would look like with the aerial view. Again, you have kind of a steeper area in this piece and it kind of flattens out. And then again, the top side is pretty flat. But again, there you have your little valley through here that's going, and then another peak on the other side of the saddle. Creeks, draws, and ridges. So if we have like a ridge line running through there, you will see how the ridge line, kind of makes this U shape as it's climbing up in elevation, right? Whereas the stream, if it's going down the hill, is making this V shape, right? It's showing this sharp incline of just going straight down the hill, because again, it's kind of making a V, a physical V. If you were to make a V with your fingers, you would be pointing your tips of your fingers down towards the ground, right? Because that's what like a stream is doing. There's just a V in the middle of that stream, or a ridge. You'd be pointing your fingertips up in the air, connecting your hands together to make that V. So that's a upside down V, or a little house, right? You're making that ridge. And then what we have is depressions, right? Depressions make like a kind of like a concentric circle around an area. So you know that the area is just, falling like a hole area. You have, 90 here, 80, and then all of a sudden you have a 60, elevation of 70 feet, sorry, and then elevation of 60 feet. So it's making that circle or depression. If you want to quiz yourself, I'll take a look at this for a quick second and see if you can match up to what is what. So like, what is A to the numerical numbers there? What is 2 to any of the, or sorry, alpha, sorry, what is the numerical matching up to the alpha numbers there? And then see if you can figure out which is which. Take just a quick second, see if you can figure that out. I'll show you the next slideshow. All right, so right here, I mean, I'm sure if you were witty enough just to look on the left-hand side, you saw that my slideshows were already popped up. But if we go look at this, try to match these up, we could look at by the contours and the plan profile here. We could say, all right, we look at one, how steep it is on this backside. And obviously we can match it up with B here. I mean, that matches the characteristics there. And again, we have that flatter slope, that bowl that comes out here, and it's a little flatter here. I mean, yeah, number one looks like B. Number one looks like B here, right? All right, and then again, go on to 2, and we see that representation of kind of just a flat, kind of sort of flat through here, but it's getting steeper, and then obviously it just peaks up real fast in here. Well, I mean, the only thing that really does that on both sides is E, right? We got that steep here, the only little small part is kind of a tiny bowl, And you can kind of see that right here in this whole piece. And then same thing with three. You got threes. We got two, a saddle, right? And it's not as steep, right? As or I guess the valley or part is not. It doesn't drop down tremendously, right? It's and you can see how further away this contour is on the top. So it's a little flatter up there. We got a more of a flat surface at the top in between the two saddles. So that would look like a D there, right? Number four, same thing. We got a backside on this, left-hand side of the plan side. It's super steep and it flans out here. Well, the only one that's doing that is C, flatter, flatter, and then gets steeper, steeper. But you see that backside just going straight up. And then we got five, same, kind of the same opposite direction. And that looks to me like F, right? You got that nice gradual slope up, and it's pretty flat at the top, but that's pretty steep at the backside. And then number six is going to be A, right? You got the two saddles, but you have a way much more V or slope, steep slope through that valley piece. And you can see that here, as you can see the valley, or you can see the contours start to get real close right there, and then it just drops off, and then there's just nothing in between because it's just flat at the bottom. But then it climbs at the top, and you can see how close those contours are. So it's just a little bit, that hillside's just a little steeper than what would D look like. All right, so this is like a USGS map, and then so as you look at this USGS map, you have what we call like anything that ended in 0 or 5 is what we have contour intervals. So you can see representations. You have 1700 here, right? You have 1650 here, and you can see right here it's getting pretty dang steep out through here. It's kind of flat in this little piece, right? And then again, from here to here, it's it's about 10 feet in distance right here, or sorry, 10 feet interval. Sorry, yeah, 10 feet in elevation difference, not horizontal distance, elevation difference. You can see it's kind of flat in this piece. It's all kind of flat in this little area between these two roads of South Hill Road and this other road. And then again, you have benchmarks, right? You got these benchmarks that are BM benchmarks that are set for you throughout this, so you can kind of just understand where to come off of if you needed to, or kind of find that your bearings there between this Murray Road and South Hill on this USGS map. All right, another pop quiz. What is A, right? What would you consider B? And let me see here if I can make it small like that. All right, what would you say A is? What would you say B is? What would you say C is? What about D and E? I'll give you a quick second there. Maybe just press pause on the video and just write them down real quick for yourself. See if you can figure them out quickly. All right, and then let me pull it back just so you can see what page I'm on. But anyways, next slideshow. So A, we would consider to be a depression, right? With that, you can see that, how these little ticks are going inward on that contours line. This darker line that you see here, that's what we would consider a major or index contour. These other ones you consider just a minor contour label or contour line. And then C, you got the two hillsides. You got those, that's a saddle. D, you got the stream, right? You got that downward V going. And then E is another stream through here. And then F, was F on there? Or was F? Well, I believe F should have been labeled. It isn't still labeled here. Oh, darn. That was labeled here. Nope. It is not. Dang it. Thought I would have had it labeled, but I do not. But F would be the ridge line, and that would be, well, this is E. It's another stream. That's another stream. That's another stream. And then it just doesn't show it where I wanted to. Yeah, so does the other one have it? And obviously you can see it. So as you can see it here on this USGS map, that's a stream. but I was hoping that maybe this one had the kind of a ridge. This one's all kind of just a kind of in this area. It's another downward V, so that's kind of another depression or valley through there. Didn't have another one. Nope, I didn't have another one. F was supposed to be a ridge, but it wasn't labeled or shown on that. Sorry, guys. All right. So those are contours. Jump over to map scales and ratios. So we got, or we say similar triangle geometry, right? Because we need to kind of break it down into that scale and ratio. So map distance, and the ratio of ground distance. So ratio of units on maps to units on ground. So like 1 inch equals 20 feet means 1 inch on map represents 20 feet on the ground. So let's say a unit slit ratio of 1 to 2,400 is 1 part on the map is 1 part on the ground. So it means 1 foot on the map is 2,400 feet on the ground, right? That's a unit slit ratio. So if you see those USGS maps, those were considered unit slit ratios. If you put like a units like P to that, that's what you would consider, right? One foot on the map is 2,400 feet on the ground. The scalar, the smaller the denominator, the larger the map scale. So again, 1 inch equals 30 feet. So map is twice the size as a 1 inch equals 60-foot map. So it means, kind of like when you scroll or kind of when you hit like control and zoom on your wheel here, like what I'm doing right now, you can see the bottom percentage that's climbing up, right? And then I'm bringing it down, I'm climbing back down, right? That's kind of the same thing of the representation of a map scale is 1 to 30, you're enhancing kind of the smaller details of it, whereas 1 to 60, you're trying to fit more into the map. So you need to make it a little, the ratio bigger so you can fit more data or information, or maybe just the size of the area itself requires that 1 to 60, where a 1 to 30 is a smaller area that you're mapping or labeling. So if a distance is 1 to 40 on the map, how far is it on the ground, right? That'd be 0.103.2. And then again, how did you figure that? Well, you take the units, right? And you go 5 divided by 12 times that 1. Oh, sorry, divided. So if you convert this over, right, and go try to convert that over to feet. So that would equal in decimal 0.25. And then you take that and divide it, or you go 0.258 your inches because you're trying to find feet. And then you take that 2.58 divided by your 0.025, you get that 103.2 feet. All right. So now on the other side of it, if the change in elevation between 2 points is 12.5 feet, what is the slope on the ground? Well, 12.1%. Then that would, again, if the elevation is between those two points. So again, you got 103, right? And then you have 12.5 feet. Your rise over run. So that's 12.5 divided by 103.2. Yeah. You go 12.5 divided by 103.2 gives you the answer of 12.1%. So without the percentage sign, that would be 0.121. Right. And national map accuracy standards, horizontal accuracy, so no more than 10% of well-defined points be in error. So if you have a 1 over 30 inch of map scale, so that means, or 0.8 millimeters of the map scale. Okay. For a USGS map, so 1 inch equals 2,000. that would equal to 66.7. For a one that's 1 in 40 for design survey, that would be point 0, point 8 tenths of a foot. National map accuracy standards, vertical accuracy, no more than 10% of the test points shall be more than half the contour interval. So if you have a 1 foot contour interval, so you would do select spot checks and you would get, plus or minus half a foot is the error allowed. So there's the way of methods of locating contours. There's what we call the direct trace contour method. That would be something like this, where you have a grid system set up, and then that grid system, you would just, establish these grid points, and you would trace like that 454 to 455, 4 to 55 here to get that contour interval, right? That's what a direct method would look like. And a couple examples that we can do like that was what we have, like Kiger Stadium here in Clown Falls. A couple seniors, my junior or sophomore year, did this topographic survey, and they did a direct method, did a complete topographic survey of the outfield and infield, and they, established all the elevations and everything, kind of using this method here, doing all these grid pattern. And that's kind of the traditional sense of professional land surveyors nowadays, where they do a grid method. They do, they go 30 paces by 30 paces, and then they just go down, and then they take measurements every 30 feet or maybe every 40 feet, and then they come over for another 40 feet and they go up. And again, it's just a grid method that they're collecting all the data. And so, and then kind of something like this topographic survey of the track stadium at OIT. It's another grid system that we did. Actually, our company did a survey for when they wanted to reestablish or redo the track and everything. And yeah, it was a pretty intense survey, because we had to, one, make sure that this was going to be draining correctly. So we had to make sure our grid system was very tight, but even tighter had to be the track itself, because we needed to be we had to do a grid system of every 25 feet on the straights and every 10 feet on the curves here, to make sure that that was going to be very accurate representation for the design team, to make sure that it was going to be a collegiate, official collegiate track for meets and championships, what have you. And so, yeah, it was a pretty intense topo for our company when we had to do something like that. This digital copy is a different senior. This is not ours. This is another senior that did a different project way back when. So you guys have already kind of done a topographic survey with the profile leveling, where you start at a known benchmark with known elevation, obviously, and then you go to you go to your certain next benchmark. And as you're doing that, you're taking these intermediate foresights, right? And then you're going from station 100 to 500, and as you're going down that, every 50 feet, every turning point, every half station turning point, you're taking these side shots, and you're establishing these elevations. And so that direct or trace method would look something like this, representing, right, your shots as you're going from there to there. You're taking these shots, and then you're doing the trace, right, to get that contour interval. So you're figuring out where your 300 is, where your 302 is, where your 304 is, those elevations, and then you're just doing the direct trace method across that. And again, this is all by hand, which is very outdated. We don't really do that anymore. What we do now is what we call the interpolation method or indirect method, where again, you set up on a site, on a point, backside another point, and then you just take measurements. And again, you can do it in that grid pattern, however it is, or radial surveying, as they say it. But you just you would do it in a grid pattern, and then you would build a triangulation network. And then so it would establish like this, and that triangulation network would give you points and interpolate elevations in between those points that you tied in. That's why you want to establish some kind of consistent grid pattern, whether it's 30 by 30 feet, 40 by 40 feet. The traditional method, most surveyors do not go over 50 feet, unless it's just kind of just a vague, just super, it doesn't need to be very accurate type of topographic survey. But in our office, we don't go anything past 50 feet on a grid system. Uh, so there's different ways to generate these contour data, and especially nowadays with technology, we have the digital elevation model, which is and digital terrain model, which looks like this up here, this image here, digital elevation model, digital terrain model, is what that represents. And then the current slideshow we're on would be what we call a tin network, or a tin a triangulated irregular network, where you use these points that you came up with from your topographic survey to establish these elevations and then these tin lines would interpolate in between these points. Another example would be kind of like, again, radial surveying. You got these points everywhere, and you start just tracing lines through them. So you go, from 82 to 71, and then you build another one, and you build more, and you kind of connect these lines. And again, remember, these contours lines don't cross. So you just got to figure out, where this is the flow is going, especially if you're out in the field yourself doing it. And then you start building your contours in that method here. And then again, contours are smooth. They're smooth lines, they're not these jagged edges. So you want to start smoothing them. So again, you start, building these contour lines. But as you can see, they're very, if there's not a stream or a ridge there, they don't build like that. So your end product would kind of look something like this, where you have smoother lines in that area. But again, if you have like a stream that runs through there, or a ridge or a valley, yeah, they do kind of start making that B, but not in that sharp, just vertex type style. It's more of a smoother area. All right. So one more thing to cover. That's the end of my slideshow here. The one more thing to cover here is where is it? There it is. The characteristics of contours, just to make sure that we're on the same page here. And this is chapter 17, section 0.6. So although each contour in nature has a unique shape, all contours adhere to a set of general characteristics. Important ones, fundamentals to their proper field location and correct platting are listed. So contour lines must close on themselves, either on or off a map. They cannot dead end. Contours are perpendicular to the direction of maximum slope. The slope between adjacent contours is assumed to be uniform. Thus, it is necessary that breaks, like grade break lines be located in topographic survey. The distance between contours indicates the steepness of slope, right? Wide denotes gentle, close spacing is steep, even and parallel spacing, uniform slope. Irregular contours signify rough, rugged country. Smooth lines imply more uniform, rolling terrain. Concentric closed contours that increase in elevation represent hills. A contour forming a closed loop around a ground is called a depression contour. Spot elevations, or I forget how to say that, hierarchs inside the lowest contour and pointing to the bottom of the hole or sink with no outlet, making map easier reading. Those little tick marks that we saw on the slideshow. Contours of different elevations never meet except on vertical surface, such as a wall, cliff, or natural bridge. They cross only in rare cases of a cave or overhanging shelf, but again, that's not really something that we much do. Knife edging conditions are never found in natural formations. Number 8, a contour cannot branch into two contours of the same elevation. Number 9, contours crossing a stream point upstream, form V's. They point down in the ridge, forming U's when crossing a ridge crest. Number 10, contour lines go up in pairs, valleys, and along the side slopes and sides of steep ridge top or sides of ridge tops. 11, a single contour of a given elevation cannot exist between two equal height contours of higher or lower elevation. For example, an 820 foot 820 foot contour cannot exist alone between two 810 or two 830 contours. And then cuts or fills of earth dams, levees, highways, railroads, etc., produce straight or geometrically curved contour lines with uniform or uniformly graded spacing. Contours crossing cross sloping or crown streets are typically B or U shaped. So keep that in mind when you're doing topographic surveys on roads. So a couple announcements. I will be posting homework number 2 this week, and that won't be due for another couple weeks. But at the end of the week, I will also start putting a midterm review for you guys to look up. And it's going to be 8 questions for the midterm. So it's just going to be, just kind of what to look out for on that. I'm also going to post an older video just talking about magnetic declination. I know most of you guys, we just covered it in 161 for like a week or two, just to give you guys, just an idea of it. I just want to go over it one more time for you guys, just to have that in the back of your head. But again, I will post a video, and it's by Professor Jack Walker that he made a couple years ago, and he explains it very well. I really love his explanation on it. So I will be posting that on the YouTube channel, and I'll just put it as a magnetic declination review for everyone to just kind of watch again. And then just be on the lookout for the homework. I'll put a due date on there. Be on the lookout for the midterm review, and then I will email or send a message on Canvas for everybody to know when the midterm is, or what day the midterm will come out, and then the due date of that midterm. All right, guys, reach out if you have any questions. I know I'm getting delayed. I'm delaying on emails. I've been just really busy at work. We've been having some other personal matters going on, so I've been having to kind of pick up the load for other people, and so it's just getting a little busier and busier. So I'm just trying to maintain as much as I can. Yeah, but I will, there will be some cracks here and there, and I apologize for those that are trying to reach out or trying to have questions, and I'm not getting back to soon enough. But that is what's going on. I promise I'm not trying to torture you. I'm just, trying to balance I'm trying to juggle all the balls here, and so it's one of those tasks that I can do, but it's just going to take a little bit of time here and there. All right, guys. Just be on the lookout for those things, and we'll talk to you guys later.